Well, howdy y'all, my name is Mr. Badsey, and I am Mr. Russell's student teacher this semester. So I am a student at Texas A&M University. I'm a senior, but since I'm trying to be a teacher, I am doing it's sort of an internship in the classroom. So you may see me on a couple videos, and I'm gonna lead you through this one. So what we're doing in this unit is we're starting our unit on reactions, okay? And this is the reactions video. We're gonna go through each specific reaction. There's 5 types of reactions. We're gonna go through each one. I'm gonna show you an example of each of them. And you're going to have to go through and you're going to have to write down 5 observations for each of these reactions. You're going to follow all the instructions you're going to see on Schoology. Here we go. So when you're doing your observations, you try to always think of 3 phases of the observation. Try to think of what you can see before, what you can observe during, and what you observe after the reaction is over. Whenever you want to make your observations, make sure you think first your 5 senses. Make sure you think of what you can touch, what you can see, what you can hear. It's going to be hard to figure out what you can smell since you're online, and what you can taste. And we're not going to be tasting anything, but you can imagine what I mean. Also, things you're going to want to take a look at in your observations are these kinds of measurements you can make. Try to think of the volume of a certain liquid, or try to think of the mass of a certain solid. These are all important observations, and these should give you enough things to look for when you're doing your 5 observations right now. So the first kind of reaction we're going to be learning about is the synthesis reaction. It's when we have 2 elements, A and B, we're going to call them. We add them together, combine, and with usually a little bit of activation energy, they combine into one final molecule. Okay. So in our case here, we're going to be combining magnesium with oxygen from the air. Remember, this is an element, even though we say it's diatomic as a gas. This is still an element. These 2 elements are combining to form magnesium oxide. Now in your Schoology, make sure that you're going to have to balance this equation by putting coefficients, and you're also going to want to put the state symbols. You're going to want to tell me what state are each of these in. Are they solids? Are they gases? Are they liquids? Make sure you take a look at that on your Schoology as well. Okay. So now what I'm going to do, I'm actually going to do it. And this is a pretty spectacular reaction. Let me get my goggles real quick. So what I have here is this is my strip of magnesium. You can see that. It is just a silver piece of metal. Okay? It's a little bit dull because it's already been reacting with the oxygen in the air very slowly, so it's not super shiny. And I'm going to mass it on my little scale, and we see it is 0.01 grams. That's how much it weighs right now. And what this is just a little ceramic plate. So what this does is this just insulates the table from the heat that's going to be generated. Now what I have here is a Bunsen burner, and it's on, and I'm going to take my magnesium and I'm going to give it a little bit of activation energy by putting it in the Bunsen burner. And I'm going to be careful not to look directly at it because you'll see what happens in just a second. Here we go. Okay, you see that? See what's happening? Okay. Now we're done. And if you can see that, you can see there is some white powder left behind. That's my magnesium oxide. Matter of fact, I'm going to weigh this, and I'm going to see this actually weighs 0.02 grams. So we can see that its mass went up because it reacted with the oxygen in the air. This kind of further proves the law of conservation of mass actually works in real life. Okay, so our next reaction we're going to be looking at is a decomposition reaction. Okay, so kind of in the same way that our synthesis reaction was 2 elements combining to become one molecule, now we're taking one molecule and it is going to break down into its constituent elements. So we generally say that as the molecule AB yields A plus B. And what we're going to be doing in our reactors, we are going to be decomposing hydrogen peroxide. H2O2 is going to break down to yield H2O, which is water, and oxygen gas. Okay. Now, this actually happens at room temperature, but it happens very slowly. And as you'll see, it decomposes, but it's not very spectacular. So we use a catalyst, iron 3 nitrate, and that's going to expedite the rate of reaction. It's going to make the reaction go a lot faster. Okay, so here I have my hydrogen peroxide. And you can actually buy hydrogen peroxide at the store. It actually comes in a bottle similar to this. The amount you get at the store is only concentrated to about 3%. So in the store, only 3% of this whole bottle would be hydrogen peroxide. This is a special scientific bottle. This is 30% hydrogen peroxide. That's 10 times more concentrated than what you find at the store. So you got to be careful with this. If you get this on your fingers, you actually notice it'll start oxidizing your fingers. Your fingers will start turning white, and it hurts a lot. So you got to be careful. So what I'm going to do, I'm going to take my hydrogen peroxide. I'm going to carefully open it, just like that. Into my test tube, I'm going to add about 10 milliliters. There's about 10 milliliters of 30% hydrogen peroxide. Now, if we actually look, you can't see it on your camera. Well, and it's really hard to see here too, but this actually is decomposing right now. Yeah, it's not very spectacular, is it? Yeah, that's why we have to have the catalyst. So what I have here, I have this solution of iron 3 nitrate. You can see it's kind of orange, because that's the color. And so what I'm going to do is I'm going to make some space. I'm going to be careful, because this is a pretty spectacular reaction. I'm going to take a little pipette. Okay. This is also 0.1 molar iron 3 nitrate. I'm going to add it to this clear hydrogen peroxide, and we're going to see what happens. So we can see there's a color change, and I'm going to step back for this one. Move the camera a little bit closer so you can see. You can see there's some bubbling. Try to see what other things are going on right now. Catalyst is working. And now it's starting to speed up. See a little bit of something coming off. Looks like a gas. Uh-oh, it's going to really start up now. Interesting. Now we're left with a solution of a very interesting color down there. This is a very interesting example of what a catalyst is. Okay. Now, this is not hydrogen peroxide that's left over. This actually is iron 3 nitrate. This is the catalyst that's left over. Matter of fact, if I take my hydrogen peroxide, we can see this is still the catalyst. Now, in chemical reactions, catalysts, all they do is they lower the activation energy of the mixture. They're not reactive. They provide an alternate pathway which lowers the activation energy. So this can actually be reused. I'm going to actually do that right now. Go. And if I actually squeeze that in there, see it turns black again. Because the catalyst was not used, it's still in there. And we can continue doing this again and again and again and again and again, as long as we have hydrogen peroxide, because this catalyst isn't used, it just lowers the activation energy of the reaction, causing the reaction to go off. So our next type of reaction is going to be the single replacement reaction. This is a reaction where you have one compound, we generalize it as AB, plus C is another compound, and that's going to yield AC plus B. Okay? Now this may be a little bit confusing if it's general like that, so what we're going to do is we're going to use a practical example. And we say, in our demonstration, we're going to have zinc metal, which is Zn, plus hydrochloric acid, HCl, is going to yield zinc chloride plus hydrogen gas. Okay, so you can see that the zinc replaced the hydrogen to form zinc chloride. You start with hydrochloric acid, HCl, and then the zinc comes in, kicks the H up, and then makes zinc chloride, and the hydrogen escapes as a gas. Okay? So, what we have here is I have a little test tube, and in the test tube I have some zinc metal. You can see that it's a little dull because it might be oxidized. I have here some hydrochloric acid, HCl. It's 3 molar, so it's pretty concentrated. It's not as concentrated as it gets, but it still could be dangerous. That's why we're on safety goggles. And we're actually going to see how this works. And this is a balloon I'm going to do to catch the hydrogen gas that comes out of this reaction. Okay? So I'm going to add about 10 milliliters, and this is about 10 grams of zinc. I'm going to add about 10 milliliters of 3 molar hydrochloric acid. We're going to see what happens. Okay, so you can see that stuff's happening. I'm going to add my balloon. Okay, so what observations can we make here? What's happening in here? Well, that's what's happening up here. Two different things are happening at the same time. Cap this to be safe. I notice it's getting a little bit warm. We'll be okay. So you see the reaction is proceeding. What's happening is, again, the zinc metal is replacing the hydrogen in the hydrochloric acid. Now in your notes you might see something about the activity series. And what that means is there are some elements that are more reactive than others, and what's going to happen is the elements that are higher on that activity series are going to replace the ones that are lower. So in this particular example, we see that zinc, if you take a look at your activity series, zinc is higher on the activity series than hydrogen is. So zinc is going to replace hydrogen. Okay. Now if that confuses you, don't be too worried about it, because that usually requires a table. You're not going to have to memorize that. What we can see is that after this has been going for a while, we can see the reaction is still bubbling. Okay. What's happened to the zinc metal? You might be able to see that in there. The zinc metal may have changed color. The balloon is filling up. I'm going to agitate that a little bit to make sure it reacts. Okay. And so there we can see the single replacement reaction. Zinc metal plus hydrochloric acid gives us a little bit of heat. Zinc chloride, which is dissolved in solution, and hydrogen gas. Okay, so our next kind of reaction is going to be the double replacement reaction. It's very similar to the single replacement reaction, except in the double replacement reaction you have two molecules, we'll call them AB and CD. They're going to react, and they're going to switch ions, parts of the molecule, and they're going to form AC and BD. Okay? So you see here B switched with C right there. We call that double replacement. Okay? And so in our example that we're going to be doing, we have lead 2 nitrate and be reacting with potassium iodide. That's going to be yielding lead iodide and potassium nitrate. Okay? Now, the thing to remember about double replacement reactions is that there's always going to be one species that we say precipitates out of solution. What that means is that right now we have our two solutions. Here's my potassium iodide. You can see it's colorless and it's clear. Nothing in it. It seems like it's just water. And in this beaker we have lead 2 nitrate. Again, colorless and clear. You can see through it. It seems like both of these materials are dissolved in solution. That's because they are. That's why we can't see them. Okay? They're colorless and clear because they're dissolved in solution. Now what's going to happen is one of these, whenever we actually react them together, is going to precipitate out of solution because one of the products is not soluble in water. So it's not going to be able to dissolve in water like potassium iodide is dissolved in here, and like lead nitrate is dissolved in here. And it's pretty cool when we actually see it. What I'm going to do is I'm going to take my test tube. I'm going to pour some potassium iodide solution in. Okay. And now I'm going to take a dropper of my lead nitrate. By the way, this is about a 0.01 molar solution of potassium iodide. And this is about a 0.01 molar solution of lead nitrate. Okay? And now, add just drop by drop, and watch what happens very slowly, even drop by drop. You see that? That was just one drop. 2 drops. 3 drops. 4 drops. And I'm going to squeeze the rest in all at the same time. Ready? You can see instantly it turns this strange color. Okay. Now what happened here is that one of the products in this reaction is not soluble in water. And that's what we see when we see the yellow. The lead iodide is yellow in color and it does not dissolve in water, and so it appears. It falls out of solution just like that. This is the double replacement reaction. Remember, there's a lot of observations I have for this one, so make sure you guys try to get at least 5. Alright, so the last kind of reaction we're going to be talking about in our basic kinds of reaction is the combustion reaction. So you can see in the general form it says that we start with a hydrocarbon, or a molecule containing carbon and hydrogen atoms only. Will react with oxygen gas to form water and carbon dioxide. And as the name suggests, it always comes with a big explosion or with a big fireball. So in our current example, we are going to be economical, and so this is the hydrogen gas we collected from our single replacement reaction earlier. So this is the reaction's calmed down. You can see the zinc's all black now because it's reacted. And in here is all my hydrogen gas. Now, if we look at our equation, we see that our fuel right here, we're not using a hydrocarbon. We're just using hydrogen gas. This will still work. This is still a combustion reaction. You can see we're starting with hydrogen gas, H2, the diatomic. It's one of the diatomic gases, plus oxygen gas, and with a little spark, a little activation energy that will result in water vapor. So, let's try it. I'm going to take... Now we're going to take our super high-tech match on a stick and see what happens. Are you ready? 3, 2, 1. 2, 1. That's that. That's the combustion reaction. Make sure if you did not see the parts you needed to observe, make sure you come up with 5 observations. There's a lot of things to observe there.